Hello, I'm Luis Serrano and this video is about restricted Boltzmann machines or RBMs. RBMs are a very powerful algorithm, mostly used for unsupervised learning and dimensionality reduction, but also very useful in generative machine learning. First, let's start with the mystery that I would like you to help me solve. Here's the premise. Across the street from us there is a house where people sometimes come to visit. We eavesdrop and notice that normally 3 people come in whose names are Aisha, Beto, and Cameron. But the 3 of them not always show up. There are times where only Aisha shows up, other times it's only Beto, and other times it's only Cameron. Sometimes more than one of them show up, say sometimes Aisha and Cameron both show up, other times it's Beto and Cameron. And any possibility is valid, including some days where none of them show up, or some days where the 3 of them show up. So let's say we start watching them every day and checking who showed up and who didn't. For example, the first day, Aisha and Cameron showed up and Beto didn't. The next day, Beto showed up and Aisha and Cameron didn't. And we start noticing that those are the only 2 things that happen. Either only Aisha and Cameron show up or only Beto shows up. And that's interesting. Why would this happen? Well, our first reaction could be that maybe they know each other and that Aisha and Cameron are very good friends, but they don't get along with Beto. However, after asking them, we found out that the 3 of them actually don't know each other. There is no relation between them, so we have to find another reason. Can you help me think of reasons why this pattern of appearances would happen without them knowing each other? Feel free to pause the video and think of possible scenarios. And here's a possible answer to our dilemma. Let's say that they're not alone. In the house, there is a dog called Descartes and a cat called Euler. And sometimes the dog shows up and sometimes the cat shows up. And it turns out that Aisha and Cameron absolutely love dogs, so they show up whenever Descartes show up, but they don't like cats. And Beto, well, he adores cats, but he's allergic to dogs, so he only shows up when Euler shows up. And when we look at the data, we conclude that the times where Aisha and Cameron showed up, perhaps it's because the dog Descartes was there, and the times where only Beto showed up is perhaps because Euler the cat was there. So let's throw in some numbers here and we'll see the significance of them later. Let's say that the amount that Aisha likes dogs is 2 since she likes them, and so we'll write the number 2 in the edge that connects Aisha and Descartes, and the amount that Aisha likes cats is -2 since she doesn't like cats, so we write it here. For Beto we do the same thing. Let's say that he's allergic to dogs, so he really cannot be around them, so we get a -4 here. And for cats, it's a 4 because he absolutely loves them. And for Cameron, it's 2 and -2, just like it was for Aisha. Now we need to add a few more numbers. We need a score for each of the participants, which tells us how likely it is that someone shows up independent of anything else. And to keep things simple, let's say that each of the 3 humans has a score of 1. But for the pets, however, it is more likely that the dog shows up than the cat. So we'll give Descartes a score of 2 and Euler a score of 1. And to add some technical terms, since we see that the people are showing up or not in our data set, we call those a visible layer. And since we don't see the pets, we call this a hidden layer. So the pets, we kind of have to imagine them to be able to explain why our data behaves the way it behaves. This is an example of a restricted Boltzmann machine, or RBM for short. In the RBM, we have nodes on the top and on the bottom, and scores for each node. The bottom ones are called the visible layer, and the top ones are called the hidden layer. None of the nodes in each of the layers are connected to each other, but every node from the visible layer is connected to every node in the hidden layer, and each edge has a value or weight. And again, the reason they're called the visible and hidden layer is because the visible layer is the one that we see in our data set, the one that we have to explain the behavior of, and the hidden layer is the one we don't see, is the one we have to imagine to be able to explain the behavior of our data. So again, in the example, our visible layer were the people and our hidden layer were the pets. Now what we want is to figure out how likely some scenarios happen. So let's score each scenario in order to compare them. What we refer to as scenario is the event of some of these people and pets showing up. Each scenario will have its corresponding score. So for example, a scenario could be that they all show up, in which case we have the scores for all the participants and for all the pairs of participants. The score is then the sum of all the scores we see here. If we add up all these numbers, we get a 6. So the scenario has a score of 6. Let's look at another possible scenario. This is when only Aisha, Cameron, and Descartes, the dog, shows up. The score of this scenario is given by the scores of its participants plus the sum of scores of the couples in this scenario, which is 8. Notice that this scenario is more likely than the previous one, which scored 6. This is because this is a likely scenario, as we have already agreed that Aisha and Cameron like dogs, but Beto doesn't. Now, how about an unlikely scenario? An unlikely scenario is, for example, this one, where only Beto and the dog Descartes show up. This is unlikely because Beto is allergic to dogs. And the score of this one is 2 plus 1 plus minus 4, which is minus 1. Notice how low is this score. So if we do this for all the 32 possible scenarios, we get the following. Feel free to pause the video and check that these are all the score for the scenario. So in the left column, we have each scenario. For example, A is for when only Aisha shows up, and the last one, A, B, C, D, E, is for when all of them show up. Now let's look at the more likely scenarios, which are the ones with the highest scores. These are BE for Beto and Euler with a score of 7, and ACD for Aisha, Cameron, and Descartes with a whopping score of 8. And the most unlikely ones, well, there is BD for Beto and Descartes, and there is ACE for Aisha, Cameron, and Euler, the cat, with a score of -2 and -1 respectively. Now, throughout this video, I will also be showing you the formulas behind an RBM, but these are not necessary to understand the concept of an RBM. The example is the main thing. But here are the formulas. So in an RBM, we have something called the energy, which is the negative of the sum of the scores of the weights times the states of the visible layer, plus the same sum for the hidden layer, plus the sum of the scores of the hidden times the visible layer times the weights of the edges. Now, why negative? Well, because we use a score, but physicists use the energy of the system. And the energy is the negative of the score. You can see this as a model with particles that have a charge and interact with each other. Some interact positively, some negatively, and they all affect the energy of the system. But again, for the purpose of this video, we will be using the score. Now, since we want to figure out how likely some scenarios happen, let's turn these scores into probabilities. And of course, we want high scores to correspond to high probabilities and low scores to correspond to low probabilities. So here's a simple way to turn scores into probabilities. Let's say that we have 3 scenarios with scores 3, 2, and 1. And we want to turn these into 3 probabilities, which are highest for the scenario score 3 and lowest for the scenario score 1. So a natural way is to think the following. Since probabilities are supposed to add to 1, let's make these scores 3, 2, 1 add to 1. How do we do this? Well, their sum is 6. So if we divide all of them by 6, we get 1/2, 1/3, and 1/6, which now add to 1. And notice that they do satisfy that the higher the score, the higher the probability. Now, does this work all the time? Well, unfortunately, no. What if we had scores of 1, 0, and -1? Their sum is 0, so we know we can't divide by 0, which means that the trick won't work all the time. But that's no problem. We can fix this. What is a way that we can avoid zeros? Is there a function that turns every number, no matter how positive or how negative, into something positive? Well, the exponential function works. So let's pick e to the x. It doesn't really matter what we pick as an exponent, but e is pretty standard, so let's go for that. So what we do is e to the 1, which is around 2.718, e to the 0, which is 1, and e to the -1, which is around 0.368. And now we can divide by the sum to make sure they add to 1. So their sum is around 4.086. We divide everything by the sum, and we get 0.665, 0.245, and 0.09. Notice that these 3 do add to 1, and notice that the higher the score, the higher the probability. So we'll go with those. This method may sound weird at first, but it's pretty standard. I guarantee after you see it many times, it'll look pretty natural, and it's called a softmax. So now, this is what we do. We take our 32 scenarios on our RBM, put them in the first column. Then the second column, we put the scores. The third column has e to the scores. And finally, the last one has the probability obtained by taking the sum of the third column and dividing all the third column by that sum. Some of them say 0. Nothing is really 0 here, but they're just so small that they get rounded to 0. So please bear with me on that. And the fourth column is supposed to all add to 1, since they are the probabilities of all the scenarios. and we know that for sure some scenario will appear, so the probability should add to 1. They don't over here because of rounding, but you can imagine that the real values do. And now let's look at the most likely ones. These are BE for Beto and Euler with a score of 7 and a probability of 0.17 or 17%. And ACD for Asia, Cameron, and Descartes with a score of 8 and a probability of 0.45 or 45%. And what about the least likely ones? Well, they are BD for Beto and Descartes with a score of -2 and ACE for Aisha, Cameron, and Euler with a score of -1. Both have probability of something so close to 0 that it got rounded down to 0. And here are the formulas. We have the energy and the probability of a scenario VH, where V is the visible layer and H is the hidden one, is 1 over Z times e to the negative of the corresponding energy. Z is simply the partition function, namely the sum of all the elements on that third column, which is what we divide by to get the probabilities. Okay, now that we have connected scores and probabilities, we are getting ready to train these RBMs, namely to find the weights that will give us the probabilities that fit the data best. But before, let's figure out what we want from the RBM. And let's revisit the relation between weights, scores, and probabilities. Let's start with some random weights on our RBM. Say for simplicity that they're all 0. Now, what probabilities do we get for our scenarios? Well, here we have our 32 possible scenarios, and here are their scores, which are all 0, since we're adding a bunch of zeros for all of them. And here is e elevated to the power of the scores. Since the scores are all 0, then e to the 0 is 1. And finally, we normalize, so we divide them all by their sum to get them to add to 1, since they're probabilities. This sum is 32, so if we divide them all by 32, we get uniform probabilities. That means that given this RBM, it is equally likely to find any of the scenarios. But there's too many numbers here, so let's draw those bars for simplicity. Now, as I mentioned, this RBM gives each of the 32 scenarios an equal probability. But we don't want that. We want something that mimics our data. We look at our data and we see that most of the time either Aisha and Cameron show up or only Beto shows up, without knowing anything about the dog Descartes and the cat Euler. So at the end of the day, we want an RBM that gives these scenarios a high probability and all the other ones a low probability. What are the scenarios in which only Aisha and Cameron show up? Well, they are these ones. They're highlighted in blue in the data, and notice that on the right we have all the possibilities where only Aisha and Cameron show up, because sometimes they will show up by themselves, sometimes Descartes will show up, sometimes Euler will show up, and sometimes Descartes and Euler will show up. So each one of these scenarios will turn into 4. And now, what are the ones where only Beto show up? Well, on the left they're highlighted in blue, and on the right we've also highlighted the ones where only Beto shows up and not Aisha or Cameron. So he could show up with Descartes, he could show up with Euler, or he could show up with Descartes and Euler. So what we want is for these scenarios to have high probabilities and all the other ones to have low probabilities. So that's how we want our final probabilities to look like. Actually, that may be too much to ask. What we want is that certain sums of these are high, but we'll see this later. And now that we know what we want, we are ready to train our RBM. I will show you a method called contrastive divergence, which is very useful. Let's go back to our original RBM with 0 weights, and which gives each scenario the same probability of 1 over 32. And let's start looking at our data one by one, starting at the top. The first example is one where Aisha and Cameron show up, but not Beto. So we proceed to highlight these 4 cases as we did before. And now we increase their probabilities by a little bit, so our new probabilities look like this. Next, we proceed to decrease the probabilities of all the scenarios, all of them including the previous 4. And we get something like this. Then we proceed to our second point in the dataset. In this one, Beto shows up, but not Aisha or Cameron. So we look at the 4 scenarios where this happens, just like before. We proceed to increase the probability of these 4 by a little bit to get something like this. And then we reduce the probability of all the other ones, just like before, and we end up with this. We now proceed to do this for all of our data set. We may need to do a few passes on our data set until we get something pretty good, like this. Notice that in here, the desired cases, namely those with AC and no B, or B and no AC, are assigned a high probability and the rest are assigned a low probability. And in the formula world, this is what we want. We wanted this maximum because we want to calculate the probability of observing a visible state as the sum of all the probabilities of finding V and H for every hidden state H. So to maximize this, we take the logarithm and then we take the derivative. And this derivative works out to be the difference of these two expected values, and turns out that the blue one is the ones that we are increasing and the red one is the one that we are decreasing. And are we done? Well, unfortunately, we're not. There's a small problem that we have to deal with. The problem is the following. Notice that at every point in our process, we're picking something out of a space of 32 possibilities, but that is actually way too high. There are way too many possibilities. It's not that 32 is big, it's that it is 2 to the power of 5, which is exponential on the number of nodes. To see how fast exponential things can grow, imagine if we had a bigger RBM with 200 nodes in the visible layer and 100 in the hidden layer, how many possible scenarios are there? Well, since each of the nodes can either be present or not, we have 2 possibilities for each, which amounts to 2 to the 300 possibilities in total. And 2 to the 300 is huge. It's larger than the number of atoms in the known universe. So even if we manage to store each one of these combinations in every atom, we'd still not have enough space. In formula lingo, this means that the partition function z, the sum of all the probabilities, is actually intractable. So what can we do? Are we out of luck? Well, luckily there is something we can do which will simplify our process quite a bit, called Gibbs sampling. And the way I like to see this procedure is the following way. Let's say we have a bag full of red and blue marbles, but actually most of them are red, and we want a bag full of blue marbles instead. So luckily we have an infinite supply of blue marbles we can put in the bag. But there's a small caveat. We always have to keep the same number of marbles in the bag. So something tempting would be to look in the bag, remove all the red marbles, and then replace them by as many blue marbles as we had red marbles, and we're done. But there's a small problem here, is that we can't actually look at the bag. So we need something fast that also doesn't require looking inside the bag. Do you have any ideas? Well, here's one thing we can do. Let's start replacing marbles. So let's first of all pick a random marble out of the bag and remove it. And then we grab a blue marble and put it in. And then let's take another random marble out of the bag and replace it with a new blue marble, because we always have to have the same number of marbles, right? And let's continue, and let's say we're unlucky and we remove the blue marble. And that's okay, since we're still replacing it by a blue marble. So at every stage, we're either a little better or exactly the same. And so you can imagine that if we do this for a long time, we'll end up with a bag full of blue marbles, or at least mostly full of blue marbles, which is what we want. And this process is how we are going to train our model. Let me show you how. What we're going to do, recall that we wanted to pick these 4 scenarios that extend our scenario from our data point and increase the probability of all of them. Well, instead of doing that, we're just going to pick one at random and increase the probability of that one. And then recall that we wanted to decrease the probability of all the other scenarios. Well, we're not going to do that because there's too many of them. We're going to pick one at random and decrease the probability of that one. So that's the equivalent of adding a blue ball and removing a random ball that could be red or could be blue, right? We could be so unlucky that we reduce the same probability that we increased before. But since we're doing this many times, and since there's very little probability of doing this, you can see that this gets us to a good point. So we do that now for the second data point. We select one at random out of the scenarios that extend this one. So for example, BE, because only beta showed up. We increase the probability, then we pick a completely random one and decrease its probability. And you can imagine that if we do this for a long time through all the data set and maybe loop around our data set many times, we end up with something pretty good. Now these over here are the same probabilities we had with the RBM that we started at the very beginning. And notice that indeed, if we were to pick randomly from the scenarios, the most likely one we would pick is ACD for Asia and Cameron showing up and not Beto. And the other one very likely would be BE, where Beto shows up and not Asia and Cameron. This matches our data pretty well. However, what happened with the rest? There are many other scenarios where Asia and Cameron show up and not Beto, or when Beto shows up and not Asia and Cameron. Why did all these get low probabilities? And the answer is that is completely okay, because our goal was to fit the data, which is comprised by the visible nodes, the people, and not the hidden nodes, which are the pets. We don't need to make sure of a scenario where our data represented get a high probability. We need that when we remove the hidden layer and we only look at the visible layer, that those are very likely. So what we want is that the sum of all the scenarios where only Asia and Cameron show up is high, and that the sum of all the scenarios where only Beta shows up is also high. And to verify this, notice that if we add all the probabilities of scenarios where Asia and Cameron show up, it's high. When we add all the probabilities of the scenarios where only Beta shows up, that's high. And when we add all the other ones, that's low. So it's a low probability for all the other scenarios. And that is exactly what we wanted. So what we conclude is that our RBM, however the weights are, they generated probabilities that mimic our data set pretty well. Now, I still haven't told you the whole story. For instance, how do we increase or decrease these probabilities? This is where we actually start messing with the weights of the model. Allow me to elaborate. Let's recall that this was our model where there are weights on all the vertices and edges. Now let's say that we're running the algorithm described previously, where we pick a random scenario from the bunch of 32 and we want to change the weights in such a way that this particular scenario gets a high probability. Let's look at the scenario. It contains Asia, Cameron, and Euler. Great. So let's just consider these vertices and the edges between them, and let's forget about everything else in the diagram. And we get these. Now let's simply increase the weights of these vertices and edges by a small amount. So if we throw in some numbers, this is what we get. Let's assume that we have the scenario where all the weights are 0. In real life, you'll start with random numbers, but for the simplicity, let's pick zeros. And we are considering the vertices and edges that only have to do with Asia, Cameron, and Euler, and we're going to increase those by how much? Well, let's say 0.1. This is called the learning rate, and it's a hyperparameter that we picked previously. Normally, we want a small number for a hyperparameter, as it is the length of the step our model takes while it learns. So once we increase the values, we get a model which is a little more likely to return this configuration. And recall that we also want to pick a random scenario and decrease its probability. So how do we do this? Well, in the exact same way. Let's say that now we want to decrease the probability of this scenario with Cameron and Descartes. So we proceed to only consider their two vertices and the edge between them, and we decrease them by a small amount of 0.1 corresponding to the learning rate. And we get the following. So if you have good imagination, you can imagine that as we go through our data several times, always doing these steps, we will end up with weights that mimic our probabilities as obtained previously. And are we finally done? Well, still no, unfortunately. There are some sampling problems that we have to deal with, namely the following. Recall that in the training process, we have a scenario that we pick among the ones with our condition, in this case, for example, Asia, Cameron, and not Beto, and then we select all the ones who have this condition in order to increase its probability. And then we pick a completely random scenario among the entire set and decrease its probability. However, as we mentioned before, there are way too many items in the set, and even picking one at random is difficult. And why is it so difficult? Because we actually want to pick them with their respective probabilities given by these bars over here. We don't want a uniformly random arrangement. We want to pick one where the probability is proportional to the size of the bars in the right. In this case, the larger the bar, the more likely we want that item. Because at every moment, we're actually sampling from the distribution given by our RBM. So I need to show you two things. The first one is how to pick a blue element, a random element among the blue ones, which come with the conditions given by our current data point. And two, how to pick a completely random element from this distribution. And we'll do it in a way that is pretty exact and relatively fast. First, let me tell you how to pick a sample scenario that agrees with the condition provided by the data point we've chosen. And quick recap, if this is our data point, for example, contains Aisha, Cameron, and not Beto, there are four scenarios that extend it, right? One is where neither Descartes or Euler show up. The other one is where only Descartes shows up. The other one is where only Euler shows up. And the other one is when Descartes and Euler both show up. So I'm going to show you how to pick a random one out of these four based on the probabilities given by RBM. And we're going to use a pretty important feature of RBMs, which is the sampling of independent vertices, such as people or pets, based on certain information. And this independent sampling works as follows. Let me start by assigning random variables to our vertices and edges, and I won't show the edges for simplicity. And to make this more clear, actually let's assume that more friends come over. So we have Fernando, Gloria, and Igor. And we also have more pets. This duck called Hypatia comes in. That's our extended cast. Now here's the deal. We're going to find the probability of a particular pet showing up given all the other participants who showed up. And something fascinating here, which is to find out if a pet shows up, all we need to know is which people showed up. We don't need to know anything about the other pets. These are independent events. And this is something fascinating that we're going to use a lot here. For example, let's figure out the probability that the duck Hypatia showed up. Well, it turns out that does not depend on all the weights of the system, only on the humans, so we can forget about the other pets. Now we'll look at all the humans that showed up in the scenario. Let's say we are in a scenario where only Asia, Cameron, Fernando, and Gloria showed up, and not the other two. And now let's look at the scores of the edges. So let's say that for Asia it's a 2, Cameron's a -3, Fernando's a 1, and Gloria's a -2. So Asia and Fernando like ducks, and Cameron and Gloria don't. And now to calculate the probability that the duck Hypatia showed up, all we need is the weight of Hypatia and the weight of the edges connected to her. We don't even need the weights of the humans that are connected to her. So it's the sum of these numbers over here. And these numbers add to 1. So how do we calculate the probability? With the sigmoid function. If you haven't seen the sigmoid function, it's this function over here. The formula is 1 over 1 plus e to the minus x, and it's simply a function that takes all the real numbers, positive and negative, and crunches them into the interval 0, 1. So a very high positive number gets sent to something close to 1, and a very high negative number gets sent to something close to 0, and the 0 gets sent to 0.5. So it's a way to turn scores into probabilities. And for example, we can see that for the value 1, the sigmoid of 1 is 0.73. So we conclude that the probability that the duck Hypatia shows up is 0.73. Now here's something fascinating. We can do the same thing for people. Let's say we want to calculate the probability that Fernando shows up. Well, that's independent from all the other humans, so we can forget about all the other humans. We look at our scenario, and let's say that only Descartes and Euler showed up. So given that, what's the probability that Fernando shows up? Well, let's look at the edges. It's a -1 here and a -1 here. So we're going to add the weights of Fernando and the edges connecting him to Descartes and Euler, which is this. These add to -4, and sigmoid of -4 we calculate it to be 0.018. Now that's a very small number, but we had a bunch of negative weights, so this was a negative score. So therefore, probability of Fernando shows up is 0.018. Now we can use this to pick a random sample. In other words, I'll show you how to pick a random blue sample from here, from the ones that agree with the current data point we're looking at. Let's start with a random RBM, with some random values for the weights. And let's say we're something in the middle of our training, so the weights look like this. Now we pick a new data point, which is this one again, where Asia and Cameron showed up, but not Beto. And we don't know what the deal with Descartes the dog and Euler the cat, since we only have information about the 3 people. So let's figure out, as we learned before, what are the probabilities of Descartes and Euler showing up, given that Asia and Cameron showed up and Beto didn't. Recall that Descartes and Euler don't depend on each other. They only depend on the people who showed up. That means that for now we can forget about Euler and all the edges connected to him. And also we can forget about the individual scores of the people. And since Beto doesn't show up in a scenario, we can also forget about him. Now on to find the probability that Descartes showed up. We know from before that to calculate this, we only have to add the score of Descartes and the edges coming in, which are 0.9, 0.5, and minus 0.4. And the sum is 1. And as we saw before, sigmoid of 1 is 0.73. Therefore, the probability that Descartes shows up is 73%. Now we do the same thing for Euler, and I encourage you to work it out yourself. Since the sum of these numbers is 1 minus 1 and minus 0.8 is minus 0.8, we get the probability Euler shows up is 0.31, which is a sigmoid of minus 0.8. So this is 31%. And that is how we sample. Basically, Descartes has a 73% probability of showing up, and Euler has a 31% probability of showing up. So we pick randomly from here with those probabilities. This is like flipping a coin with 73% probability of being heads, and if it hits heads, then we pick Descartes. And the same thing with Euler with a 31% probability of being heads. So let's say that we pick randomly and we get that Descartes did show up and Euler did not show up. So now we get our complete scenario. That's how we managed to pick one out of these four with probabilities given by our RBM. So this is the one we end up picking, where Descartes showed up and Euler didn't. Now we're almost done. I show you how to take a simple random scenario given the people who showed up. But now how do we pick a completely random scenario? In other words, how do we pick this red sample, which is a completely random sample out of this distribution? Now, it is very hard to pick a completely random sample out of the distribution where the probabilities are given by the bars. So I'm going to show you a pretty close approximation, a way to find a pretty random sample. And the way I like to think of it is as follows. Let's say that you're in the world. How do you find a completely random point in the world? Well, let's say that's hard because the world is too big. But you're going to have to start somewhere. So let's say that this is the place where you live. And now what you do is you take random steps. And if you take a bunch of them by walking to places that are close by, but many times, then one can assume that if your number of steps was very big, that the place you ended up was random. Of course, you need to take a lot of them, but the probability you end up may not be correct. But let's live with that. This is a pretty random scenario. And that's what we're going to do over here. So we start with our data point. Again, is the one where Asia and Cameron showed up, but not Beto. And just as I showed you before, we are going to pick a scenario that extends this one. So a blue scenario. And now we're going to take a random jump to another scenario, and then another random jump, and then another one, and another one, and we're going to take a bunch of jumps until we get somewhere that's pretty random, and that's the one that we're going to consider our fully random scenario. How many jumps can we do? Well, that's a hyperparameter and something we determined beforehand. It depends on our computational power, but normally the more jumps we can do, the more random our outcome will be. And now let me show you how to do the jumps. So the jumps are done as follows, in a very similar way, except we're going to switch between sampling from the visible and invisible layers as follows. We start with our current scenario, which is AC for Asia and Cameron. And as we did before, we can sample randomly from here and then pick the scenario where Descartes shows up, but not Euler. And now we forget about the people and we start with the pets. We start with a scenario where only Descartes showed up, and we sample from this one because we know the probabilities that each person independently showed up based on Descartes showing up. So let's say we get that Beto and Cameron showed up. So now we forget about the pets and we start with a scenario where Beto and Cameron showed up, and we sample from there and we get that we've sampled the case where both Descartes and Euler showed up. So again, we forget about the humans and we sample from this, and we get a scenario where, let's say, none of them show up. That's okay if none of them show up. That's one of the cases. So we start from here and we sample from the pets and we get that Descartes showed up, and we continue in this fashion, always alternating between sampling from the pets or from the humans, and eventually, after several steps, we end up in our last scenario where only Descartes showed up among the pets and only Asia showed up among the humans. So what we're going to do is the blue scenario, so the first step in our scenario, is going to be the one where we increase the weights. And the red scenario, so the completely random one, is the one where we're going to decrease the weights. And that actually is the end of the story. If we repeat this process many times, we will get to an RBM with weights that are good and that sample our data set pretty well. So that was a long process. Let's do a small summary. We started with some data and we wanted something that will generate samples that look a lot like this data. So with the data, we built a restricted Boltzmann machine with some weights and a hidden layer. Now this RBM encodes all the probabilities of all the scenarios that can occur. In other words, it captures the probability distribution of the original data. Now that we have the distribution of the data, we can use it to generate new samples simply by picking points out of this distribution as we saw before. A very interesting application of RBMs is in image generation. If we use as our visible layer some images such as the MNIST dataset, we can train an RBM and see that the hidden layer becomes a few different pen strokes that are related to the images underneath. And by sampling randomly for this RBM, we can actually generate some pretty faithful images of handwritten letters. And that's all, folks. Thank you very much for your attention. I'd like to remind you that I have a book called Rookie Machine Learning, which I explain the algorithms of supervised machine learning and several techniques to train your models in a simple way, the way you've seen in this video. So I recommend it to you. Here is the link to get it. It's also linked in the comments below. And there's also a 40% discount code with the code SerranoYT. You can get that discount. And as usual, if you like this video, please subscribe for more content, hit like, share among your friends, and comment. I really enjoy reading your comments, and especially if you have ideas for other videos that you would like to see, feel free to put them in the comments. This is also my Twitter handle if you would like to tweet at me. And finally, all this information, all these videos, the book, and many more things can be found at Serrano Academy, so make sure you check that out. Thank you very much for your attention, and see you in the next video.